Hi all. Today we can discuss the fundamental theorem of gradient. Okay, so we already know what is a gradient is. So gradient usually we define for scalar field. So the gradient of some scalar field phi, where phi is a function of x, y, z. In general, is written as I times dou phi by dou x plus j dou phi by dou y plus k dou phi by dou z. Okay, so the fundamental theorem of gradient says that if you integrate the gradient of scalar field over a line from some initial point A to the final point B, then that would be equal to the difference between the final point and the initial point of the scalar field. So this is what is called the fundamental theorem of gradient. Okay, so we can prove it. So del phi dot dl can be written as I times dou phi by dou x plus j times dou phi by dou y plus k times dou phi by dou z. Dot dl, so in general an infinitesimal displacement can be written as I dxi plus dyj plus dzk. Now if you take the dot product between these two, what will you get? So we have to take the product between the consecutive terms. That is, the x terms would take product and y time would take product and z terms. So it will be dou phi by dou x times dx plus dou phi by dou y times dy plus dou phi by dou z times dz. According to the differential calculus, so this quantity is nothing but the differential of the scalar field phi. So dou phi by dou x times dx plus dou phi by dou y times dy plus dou phi by dou z times dz is nothing but d phi. So that means del phi dot dl is nothing but d phi, the differential of phi. So and hence the integral from a to b, sorry, the integral from a to b del phi dot dl is actually the integral from a to b d phi. So if we integrate d phi, we'll get phi with lower limit a and upper limit b, and that is equal to phi of b minus phi of a. So that's the proof for it. So this is what is called the fundamental theorem of gradient. Okay, now the same theorem we can write in another way, or we can say it in another way as well. So the line integral of gradient is depends only on the final point and the initial point. So therefore, the line integral of gradient is independent on path. So the same theorem we can say in another way. So corollary 1. So it says the integral a to b del phi dot dl depends only on the final and initial points, and it is independent on path taken. And there is a corollary 2 as well. So if line integral is independent on path, then what would be the closed integration, or the line integral over a closed path? So line integral of the closed path would be 0. So there is a corollary too. So del phi dot dl is always 0. Okay, so we have already seen this kind of integration. The line integral is independent on path, and we have used one particular name for such vector field. Okay, so do you remember that? Yes, that is what is called conservative vector field. Okay, so for conservative vector field, because if we are denote the conservative vector field as V, then integral a to b v dot dl is independent on path, or the closed integral v dot dl is equal to 0. Okay, now by connecting these two, we can say that your conservative vector field V can always be written as the gradient of some scalar field, because the conservative vector field obeys, or it follows the property of the gradient. So therefore, the conservative vector field can always be written as the gradient of some scalar field. So therefore, a conservative vector field can always be represented as gradient of some scalar field. So that means V, I can write some plus or minus del phi if V is conservative. It can be plus del phi or minus del phi. So both plus del phi and minus del phi satisfy the same relation or the same property. Why I put minus sign is because when you're going to the electrostatics, the electric field can be written as the negative gradient of scalar potential. So there we additionally put a negative sign. This is only because the direction of electric field in such a way that in the direction in which the potential decreases its maximum. Okay, so remember the gradient gives the direction in which uh, the scalar field changes at most, that is in the increase in direction. Okay, and so negative of gradient of phi would give the direction in which the scalar field decreases fast. Okay, now the electric field would be in the direction of the decrease in potential. So therefore, in case of electrostatics, so this we will come in 5th semester. In electrostatics, the electric field is a conservative field, and the electric field we can write as negative gradient of the scalar potential phi. So here phi is called electric potential. So the direction of electric field would be in such a way that it is along the direction in which the scalar potential decreases at most. Okay, but in general, we can write the conservative field. So conservative field comes in the different context of physics. So in general, the conservative field can be represented in terms of the gradient of some scalar field. Okay, so interpretation of scalar field depending upon the context. So in case of electrostatics, the scalar field is called the electric potential. But in other contexts, so depending upon the context, we'll give some name for that scalar field. Okay, so that's all about the fundamental theorem of gradient. So next we are going to discuss the fundamental theorem of divergence in next video. So see you later. Bye.